Well, we've seen how we can find the average rate of change between 2 points on a curve. But what if I need to find the exact rate of change at a single point? What's needed is the ability to find the slope of a curve at that point. Now, one way to approach this problem is to find the slope at a specific x value by calculating a delta for x1 and x2 values that are infinitesimally close together. And you can think of it as measuring the slope of a tiny straight line that comprises just a part of the curve. To find this point, we need to understand something about a concept called limits.
Here's our function for a cyclist's distance travelled in a given number of seconds. Now, although we graph that function as a line, in reality, that line is made up of individual points that plot the x value, in this case time, against the y value, which is calculated as f of x. In this case, that's distance. So for example, here's the point showing where x is 3 and f of x is 10. Now, as we increase the value of x approaching 3, we'll find points on the line that are increasingly close to 3. So here's the point at x equals 2. If we increase x to 2.5, we get a point that is closer. And at 2.75, we're even closer. And if we keep going, moving increasingly fractional distances, we'll always end up at a point that is closer and closer to 3. Now the same is true in the opposite direction. Here's the point at x equals 4, and we can move closer, and closer, and closer to an x value that is ever closer to, but not quite, 3. So as we move in either direction, there's a theoretical value for x that's infinitesimally close to 3, which we could use as the input for the function to generate a y value for an adjacent point. Now symbolically, we call this the limit of the function as x approaches 3.